Having done the planar polar coordinates, the obvious question to ask is, what is the corresponding system of coordinates if I want to describe a three-dimensional motion? A very straightforward extension of this to 3 dimensions is the cylindrical coordinates, in which I describe the motion in the xy plane in terms of this r and phi. Notice how I have changed the orientation of x and y, and it will require some getting used to. And the third dimension is treated as z itself, so that the position of a particle is going to be given by r, which is in the plane x and y, phi and z, z giving you the third dimension. Obviously, the vector r, which is in this direction, is going to be given as r unit vector r plus z unit vector z. Let me show it more clearly in the next picture. So, I have x, y and z. The position of the particle is here, which is at a height z from the xy plane. In the xy plane, the radius vector makes angle phi from the x axis. So, this vector here is nothing but r, where unit vector r is in this direction in the xy plane, and this vector is nothing but z unit vector, and therefore, the position vector r is given as r plus z. The phi unit vector is again at the xy plane, perpendicular to r and perpendicular to z, like this. How about the velocity of the particle? Again, it is very simple in this case, because the motion in the xy plane is being given by the planar polar coordinates and the z direction is fixed. So, therefore, r dot, the velocity, is going to be equal to d by dt r plus z. You are more used to calling this k. So, I am using them interchangeably. This is going to be equal to r dot r plus, I have already derived this. So, I am going to write the result right away without any derivation, r phi dot phi plus z dot k or z dot z. There is no derivative of this because z unit vector is fixed. Rest derivation of the acceleration I will leave for you as an exercise. I will just give you the answer. It is going to be same as in the previous case for the plane in xy plane, which is going to be r double dot minus r phi dot square in r direction plus r phi double dot plus 2 r dot phi dot in phi direction plus z double dot in z or equivalently k direction. A more interesting extension is the spherical coordinates to describe three-dimensional motion, and in this case, again, if I make my x, y and z coordinate system, the position of a particle is given by its distance from the origin, the angle theta that this radius vector makes with the z axis, and angle phi that the projection of the radius vector, this is the projection I am showing again, makes with the x axis. So, now I am using r, the distance from the origin, the angle theta that is made from the z axis, and angle phi that the projection of r makes from the x axis. The unit vector r is going to be in direction of the radius, unit vector theta is going to be in the direction of increasing theta, and unit vector phi is going to be in the direction of increasing phi. You can see that the phi unit vector is confined to xy plane, whereas r and theta are going to have component in all x, y and z direction, and in the next few minutes we are going to see how these unit vectors are represented. I just want to mention here that theta in this case varies from 0 to pi and phi varies from 0 to 2 pi, and I leave it for you to sort of work out that this covers the entire space, and r obviously varies from 0 to infinity. Let us then see that I am representing a particle by vector r, this vector r, which is r again, where unit vector r is in this direction. The components of unit vector r are therefore going to be, it is very easy to see that the z component is going to be cosine theta. The projection on the xy plane of this is nothing but sine theta, and therefore the x component is sine theta, this is phi cosine of phi I plus sine theta, and the y component of this projection sine of phi j plus cosine of theta k. This is the unit vector in r direction. How about the unit vector in theta direction? Unit vector in theta direction is going to be like this. This is r, this is theta. If I transport it down, just to make it look easy, this is pointing down from the plane of x and y axis by an angle theta, because this angle is theta, and therefore you can see the components of theta in x and y direction are going to be cosine of theta, cosine of phi, because this angle is phi I, plus cosine of theta, sine of phi j, and its z component is in the opposite direction, so minus sine of theta k. Recall that r was sine of theta cosine phi I plus sine theta sine of phi j plus cosine of theta k. You can see right away that r dot theta is equal to 0. These two together give you cosine theta times sine theta cosine square phi plus cosine theta sine square phi, minus these two give you minus sine theta cosine theta, giving you this. Similarly, if I were to write the components of phi vector as I told you earlier is confined to xy plane, and therefore phi unit vector is just like in planar polar coordinates, which is equal to minus sine phi I plus cosine phi j. So I have all three unit vectors. Now how about the velocity? Velocity is equal to dr dt, which is equal to r dot r plus r dr dt. Expression for dr dt, rate of change of the unit vector, in this case is going to be slightly more complicated because now it has all three components, but we can geometrically see how this is going to be. Here is vector r. If I were to change only theta and keep phi fixed, then you can see the r unit vector is going to change from here to like this, and that change is going to be equal to delta theta in theta direction. On the other hand, if I keep theta fixed and move phi, change phi, then the r unit vector, this component is going to change, and that component is nothing but r sin theta. Since this is a unit vector, this r is 1 and is going to change by delta phi in phi direction, and therefore, the net change in delta r in r unit vector is going to be delta theta in theta direction plus delta phi sin theta in phi direction, and therefore, dr by dt is going to be theta dot theta plus phi dot sin theta phi. Therefore, the velocity, which is r dot r plus r unit vector rate of change, is going to be equal to r dot r plus r theta dot in theta direction plus r sin theta in phi direction. Let us see whether this, which we derive to be theta dot theta plus sin theta phi dot phi, can be derived directly from the definition. R was equal to sin theta cosine phi I plus sin theta sin phi j plus cosine of theta k. If I take the derivative, I have dr over dt, which is equal to d by dt of sin theta cosine phi I plus d over dt of sin theta sin phi j plus d over dt of cosine theta k, which turns out to be equal to theta dot cosine theta cosine phi minus phi dot sin theta sin phi I plus theta dot cosine theta sin phi plus phi dot sin theta cosine phi j minus theta dot sin theta k. If you collect all the terms together, you can see easily that this comes out to be equal to theta dot theta plus sin theta phi dot. The rest of the exercises, that is calculating the acceleration and finding it in terms of theta, phi and r, I will leave as exercise for you. To sum the lecture, I would like to tell you that we covered planar polar coordinates, in which I described the motion in a plane using the radial distance and the angle from x axis. We extended this to cylindrical polar coordinates, in which I use r, phi and z as my coordinate system, and we also use spherical polar coordinates, in which I use r, theta and phi as coordinates to describe the distance or the displacement of a particle. Before we just end the lecture, I just would like to tell you how to think about spherical polar coordinates. You can think of these as two sets of planar polar coordinates, one set being r and theta, that is the particle moves in z and this plane, z and this plane of this line, z axis and this line, with this angle being theta and this r. This describes one set of planar polar coordinate, and the other set being in the xy plane with this being r sine theta and this angle being phi.